I was hiking a while back, deep in the forest where it's pretty dark, and my eye caught this flash of intense metallic blue.
Oh, wow.
Yeah, and my first thought was, okay, that's trash, a piece of plastic, maybe a lost earring or something.
Hmm.
So I walk over, and it's this tiny, hard berry on a plant. The sheer intensity of the color in that deep shade was just stunning.
Okay, let's unpack this. Today we're diving into Pollia condensata, the marble berry. It has, I think, one of the most intense and durable structural colors ever found in biology.
And that's the key word right there, structural. What's so amazing is that this berry is intensely blue, but there's absolutely no blue pigment in it. None.
No pigment at all.
Not a drop. The color is purely an effect of the nanoscale architecture inside the fruit's own cell walls. It's physics, not chemistry.
So we're talking about a kind of natural advanced engineering happening in the skin of this fruit. What's the fundamental building block here?
It's cellulose microfibrils. I mean, we're talking about the single most abundant biopolymer on the entire planet.
Just plain old cellulose.
Exactly. But it's how that cellulose is organized. It's arranged in these incredibly dense microscopic layers.
And how are those layers stacked to create such a specific, brilliant blue?
They're stacked with a twist. Imagine a tiny microscopic spiral staircase.
Okay.
Each layer of cellulose fibers is rotated just slightly from the one below it. So as you go deeper into the cell wall, the fibers create this perfect spiral, this helicoidal structure. And if we connect this to the bigger picture, that structure acts like a perfectly tuned biological mirror. We call it a photonic crystal. The spacing in that spiral is just right to interfere with light and reflect only one narrow band of color, in this case blue. It's a phenomenon called Bragg reflection.
Okay, here's where it gets really interesting for me, though. You said it's a perfect reflector for blue, but when you look at pictures, the fruit looks almost pixelated. You see speckles of green and even purple. Why isn't it just a uniform blue?
That's such a great observation. That mosaic look is actually key to its success.
Ugh.
The thing is, that spiral's pitch, the tightness of the twist, varies just a tiny bit from cell to cell.
Ah, okay.
So since the pitch determines the exact wavelength, each individual cell acts as its own colored pixel. One cell reflects a perfect blue, its neighbor might be tuned to green, the next one to purple, it makes the fruit glitter.
And then there's the whole polarization thing. A lot of structurally colored insects, they do one thing, but this berry, it's doing two different things at once.
It is, which is unique. These spiral structures have what we call a handedness. They can twist to the left or they can twist to the right.
Left-handed or right-handed.
Exactly. And the berry has a random patchwork of cells reflecting left circularly polarized light right next to cells reflecting right circularly polarized light. It's immensely complex.
That is just, it's incredible complexity that just self-assembles. Understanding how nature builds things with that level of detail is so critical. It's actually why companies like our sponsor are so valuable. This deep dive is sponsored by Embersilk. If you need help uncovering where AI agents could make the most impact for your business, automation, integration, or software development, check out embersilk.com for your AI needs. They really help you build the future, one digital brick at a time. So let's talk about performance. How bright, how durable is this berry compared to, say, the world champion of structural color, the morpho butterfly?
The numbers are extraordinary. The marble berry reflects about 30% of the light that hits it. That actually outshines the morpho.
Wow.
But the truly amazing part is the durability. Because the color is architectural, it's locked in, it can't fade like a pigment. I mean, there are herbarium specimens collected back in 1974 that are still just as brilliantly blue today as they were decades ago.
So what does this all mean for us, for developing new sustainable materials?
It's a perfect blueprint. It really is. Scientists are already replicating this design using things like cellulose nanocrystal films or CNCs.
Right.
These little crystals self-assemble into that same spiral phase. And by just tweaking that twist, we can create pigment-free, incredibly durable, color-fast materials for textiles, for coatings, even for anti-counterfeiting measures. It's a beautiful example of green engineering.
It's just so inspiring. Nature took the most common material on Earth, cellulose, and used it to create maybe the most intense, durable, and complex color display we know of. It's a masterclass in sustainable innovation.
And that leads to a wonderful final thought, I think. The berry achieves its maximum visibility, its ability to stand out in the dark forest, not by being perfectly uniform, but by embracing that subtle cell-to-cell variability. It's a powerful lesson in what makes for a truly robust and brilliant design.
That's a fantastic insight. If you enjoyed this deep dive, please subscribe to the show.
And hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in.